2 class periods and then the final next week, Tuesday. I've just posted this note about the final exam note card. You can't have a note card on the final exam, 3 by 5 inch. You just can't have any worked examples, and you cannot have material from chapter 12. But the old material that we've already tested on, you can have definitions, theorems, formulas, stuff like that. Just no chapter 12 content at all, and no specific worked examples. If you have any questions, just email me or whatever. I also posted the content for the final. This will work under exam reviews and the final exam. So that'll give you an idea of what's on the final. Start honing your studies.
Both sides of the note card?
Yeah, you can use both sides of the note card. You can print. Some people just print the font, the text, so it's a lot smaller and neater. You can do that as well. Just got to hand it in with your exam and make sure that there's nothing's crossed out or that looks suspect. Like if you hand me a note card after the exam's over with half the stuff crossed out, that's not good. So you either type it out and make sure there's no errors, or if you made an error before class on the day of the final, say, hey, I had to cross this out. Otherwise, I'm going to assume that you used something you weren't supposed to and then crossed it out after the fact. So, there's always some things to be wary of when using a note card. I think most of it's pretty common sense stuff, though.
That's at 3 foot by 5 foot?
Yeah, that's why I say 3 inch by 5 inch. I haven't had anyone bring a note card in that large, but I certainly wouldn't put it past anybody. I've seen some clever cheaters for sure.
It's not cheating, it's aiding. It's just
No, I saw a thing online where somebody had taken a label off of those plastic Coke bottles.
Yeah.
They scanned it and then they photoshopped out all the nutrient facts, and then they put all their formulas in there where like the calories go and the ingredients, and then they taped it back up to their bottle. So they were just like, hey, yeah, here I'm looking at my Coke bottle. How did you find that? I don't remember.
that one's been floating around for like 10 years. I remember people talking about that.
They deserve to get away.
Yeah. So yeah, if you have any other questions about the final or whatever, please let me know. Are there any homework questions? We did finish 12.1. So any questions on 12.1? Good. All right, so then we'll start 12.2. And 12.2 kind of plays into 12.3. And so 12.2 is kind of just an introduction into polar coordinates. We'll see like equations of circles look different and stuff like that. And then in 12.3, our last section, we look at how do we perform calculus with polar coordinates or in the polar coordinate system. So it's just another type of coordinate system that enables us to do the same thing we do in rectangular coordinate system. So let's say we have this point in the rectangular coordinate system that's 4, 4. So instead of describing like how far we go over left or right and how far we go up or down, we can use a different way to describe the same point by describing the distance from the origin. So we can describe that distance from the origin and the angle that it makes with the positive x-axis. So we'll call that distance r, theta. So that's what polar coordinates are. It's not an x and a y, but it's an r, a distance from the origin, and a theta, an angle measure from the positive x-axis. So any point in this rectangular coordinate system can be described equally by just giving a distance from the origin and an angle that you sweep around. Does that make sense? And like if you take Calc 3, you'll look at a spherical coordinate system as well. So like you're in three-dimensional space. So not only would you have a distance from the origin, but you would have you know, an angle you go out this way, and then an angle you would go out this way. So you'd have like two different angles. But you know, one of the main benefits is certain equations, like equations for circles. Circles are like super easy to describe in a polar coordinate system. So, you know, you're working with what do they call this? Like cyclical functions, stuff like that. It's oftentimes they're easier described and worked with in a different coordinate system. So the polar graph looks like this here on the right, where each one of those concentric rings or circles represents a radius. So like this is circle radius 1, this is a circle radius 2, and so forth. And so those give us our radius, our radii rather. And then all of these rays emanating from the center are the angle measures, the thetas. So you know, this first one is, that's your pi over 6, that's pi over 4, that's pi over 3, and so forth. Just highlighting our, I think the figure below kind of shows, well, no, I don't have that. So let's talk about the point here at the origin. The origin in this setting is just referred to as the pole. That's when r is equal to 0. So it doesn't matter what your angle measure is. If r is 0, you're always right there. The positive x-axis is called the polar axis. And we can talk about, like, if the 0.44, what would it actually correspond to in terms of r theta? We'll look at how we convert. But, you know, this 0.44 is somewhere over here. But we would describe it by how far we go out from the center or the pole, and then how far we rotate, and typically in the counterclockwise direction. So somewhere over there, same exact point. I'm not sure why I have that there. So the thing with like rectangular coordinate systems is those have a unique representation. If I say the 0.44, you know exactly what point it is, and there is no other 0.44 in the rectangular coordinate system other than that point. The points in polar coordinates, there is not a single unique representation for a point. There's not a single representation or unique representation for a point in polar. Yeah, polar is fine. So why would that be? Why would we not have a unique representation?
Clockwise or counterclockwise because of the angle?
Yeah, you can go counterclockwise or clockwise depending on the angle. But specifically, if I were to say, you know, I'm talking about this point right here, and then I measure the radius and the angle here, theta.
You can have it that plus 2 pi.
Right, if I add another 2 pi to this theta, I get a different theta representation, but it is the same point. So the ways, there's a couple of ways to represent points in polar coordinates, and we'll write those down. So there's two alternative ways to describe a point. Describe the point r theta. So So one, we just said, if we take the same radius or distance from the origin, and we have theta plus 2 pi. Or we could do plus or minus, really, doesn't matter. So then we could come up with infinitely many representations for r theta just by adding and subtracting 2 pi. It's the same point. The other way is if we think about describing it this way, would be, let me just write r for a moment and then write r theta plus or minus pi. So it's not going to be r theta plus or minus pi, but what happens if I add or subtract pi to this point? Where would that put me if I add pi or subtract pi? Where would that point be?
Opposite.
Yeah, it's just the opposite. It basically reflects through the pole. Wait, 1, 2, 3, 4. So if I just add or subtract pi to that, and then I get this point over here, clearly not the same point, but if I make the radius negative, then again, that's going to reflect this thing back over here. So this point with a negative radius and a plus or minus pi to the angle moves it back through there. So I know it typically doesn't make sense to say you've got a negative radius or negative distance from the origin, but the way we can think about that is, if I said, for example, if we have this point here, let's do this one. What would that point be in polar coordinates? Yeah, so the radius, I've gone out 1, 2, 3, and the angle is pi over 6. So in polar coordinates, that point would be described as 3 comma pi over 6. Okay. I really wouldn't see the radial line there necessarily. But if I think about going out, instead of going out this direction 3 and then rotating it up pi over 6, I can go out this direction 3 and think of that as like my negative radius. But if I rotate it pi over 6 units, if I go out negative 3, let's ask the question then. It's not necessarily the same point, right? They're two completely different points. So if I'm going to make the radius negative, like I did here for this point, then I have to sort of reflect it, thinking about reflecting it through the pole or rotating it 180 degrees. So the pi over 6, I have to either add or subtract pi to that to get this same point described with a negative radius. Okay. So in other words, if you're gonna add or subtract pi, you just negate the radius. If you add or subtract 2 pi, you just leave the radius the same. Two different ways to represent the same exact point, and there's infinitely many of those. Okay. Do y'all have any questions about that? There's not a whole lot of stuff we actually do in 12.2. It's just that we're getting used to the coordinate system, and then it's really in 12.3 that we're doing most of the work. So I don't know that we'll actually cover all of these since we are a little behind, but we can certainly do a few of them. So some points there are plotted, and we're going to express the point using polar coordinates and then find a second representation for each point. I will note here on this first page that usually polar points r theta are written with r greater than 0, and theta in between 0 and 2 pi. Greater than 0. It's not that it has to be that way, but that's just typically how they're presented. More of a standard, I guess, that has been agreed upon. So positive radius, angle between 0 and 2 pi. And so we'll try to do that here in part 1 when we're describing these points. For part 2, it doesn't really matter. We'll just find some other representation for that point. And again, I don't necessarily think we need to do all of these, but let's start out with point A. So what's the coordinate for point A? The coordinates, rather. What? 4. We've got a radius of 4. We went out 4, 1, 2, 3, 4, and then rotated pi over 6, or counterclockwise. So positive radius, angle between 0 and 2 pi, 4 pi over 6. For point A, what's an alternative way to describe point A?
-4, 7 pi over 6.
7 pi over 3?
Over 6.
What do y'all think? Agree, disagree, not sure? Okay. Yeah, so this one here, -4, 7 pi over 6. We would go out -4 this way, and then rotate it 7 pi over 6 units here. As long as the angle's positive, that would just indicates counterclockwise. The angle's negative, clockwise. Let's see. How about point D?
4 pi over
4 comma pi over 2. And an alternative for the same point, point D?
2. -4, 3 pi over 2.
-4, 3 pi over 2. What do y'all think about that? -4, 3 pi over 2. Okay. How about point F?
Two comma 4 pi over 3.
2 4 pi comma 4 pi over 3.
Yeah.
What do y'all think? Okay. Alternative representation?
2.
2. 2 comma 10 pi over 3, okay. Y'all agree? Alright, so that's that. So like, you know, the non-uniqueness of these points, it can be a little frustrating when you're working in polar coordinates. You're trying to figure out where two polar coordinates intersect. You know, so there are some frustrating things that fortunately we don't really run into a whole lot. But the way we want to think about these, especially moving forward, is that the reason we actually talked about 12.1, the parametric equations, is when we start looking at polar coordinates and functions expressed in polar coordinates, we want to think about those as functions of theta, or we're parameterizing using theta. Theta is our parameter. So it kind of fits in with what we talked about in 12.1, when we think about the parameter t in 12.1 being a parameter theta, kind of lending itself to this coordinate system. But yeah, so like curves that unfold, they may not unfold, like you may see them intersect. Like if you just looked at a static graph of like this circle and this circle, you might think, okay, well, they only have these 2 points of intersection, right? But as far as a parametric equation it goes, these things could intersect at 2 completely different times, right? Like they may not coincide or trace around and hit this point at the exact same time. This first circle might have been there at t equals 5, and the second circle might have been there at t equals 7. So, there are some subtleties to this. And, the non-uniqueness of points is one of those kind of frustrating things, especially when you're trying to describe where things are at. So as far as converting between the Cartesian or the rectangular to polar and polar to Cartesian, we'll draw another point here. Just to and thinking about this in terms, we're going to kind of superimpose the XY coordinate system here. How would we convert, let's start with converting from polar to Cartesian or rectangular.
Sine theta times r?
Say that again, Greg.
It's the sine theta times r and cosine theta times r. Or is it defined?
Yeah, so you said sine of theta. Sine of theta times r. If we did r times sine of theta, what would that give us? That's the y. That's the horizontal distance from the positive x-axis. Right. So if we're given an r and a theta, we're trying to convert that to an x and a y. We're given an r, given this theta, then r times sine of that angle gives us the y coordinate, and x, similarly, r cosine theta. So that's all you need to convert from polar to Cartesian to get your x and y out of an r and a theta. From rectangular to polar. In other words, you're given an x and a y, and you want to convert that to an r and a theta. Any ideas on how to convert xy to r theta? Tangent of theta is xy. Yeah. So tangent of theta is y over x, or theta is inverse tangent of y over x. And how would we find r? R squared is x squared plus y squared. Or r is plus minus root. So you might say, well, you've got two different radius, like a plus minus 2. Which one would it be? Is it the positive 2 or is it the negative 2? and that really depends on the angle. Same thing with like a limitation we have here with the inverse tangent. The inverse tangent only outputs numbers from where to where, or angles from where to where. Yeah, from negative pi over 2 to pi over 2. So even like if you're computing this theta, it might be kind of misleading as far as what the actual angle is. So not only do you have to think about where is this point x, y in space, what quadrant is it in, when I come up with this specific angle with inverse tangent and with these two different radius or radii, you've got to like put the pieces together in the way that it describes the point you're trying to describe. If you just take the first thing that comes out of your calculator from the inverse tangent and the positive one of these, let's say, it's not necessarily going to work. Okay, convert, that's fine. Convert 1 negative pi over 3 to rectangular coordinates. So this is a polar coordinate r theta, and we want to know what it looks like in terms of x and y. So all we're doing is saying that x is r times the cosine of theta, and y is r sine theta. Okay, so we've got cosine of pi over 3, 1/2, sine of pi over 3, root 3 over 2, negative. So there's our x and there's our y. So those are, converting from polar to rectangular coordinates is pretty straightforward. When we convert from polar to rectangular, rectangular to polar rather, that's when we got to be wary of where that point actually is. So, for some of them it might be straightforward. I would recommend just drawing this out. If we're going to convert the rectangular negative 4, 4 root 3, just draw that somewhere, have a general sense of where that belongs. So that's our x and our y. Doesn't really matter what you find first. If we're going to say that r is the positive and negative square root of x squared plus y squared, we're going to get two radii out of that. Which one it is depends on where your point is and what angle comes out of the inverse tangent. So we have 16 plus 16 times 3, 16 times 4. Yeah, 16 times 4, 64. So we come up with the radius is either plus or minus 8. That's if you want to look at it, what we found is the distance that it is from the origin. There's our r. If we say distance, though, we have to strictly stick with the 8. Okay, so to determine if it's the positive 8 or the negative 8, let's look at the angle that comes out of this. The angle is the inverse tangent of y over x. So the inverse tangent of negative root 3. What would that give us?
Negative pi over 3.
Negative pi over 3 is what comes out. But we know, well, what else could it be? It's the inverse tangent's only outputting things that are over here. So we have this negative pi over 3 for this one. What else could it be? Or could it be anything else? If the tangent of y and x have to be negative, could we have an angle over here in the first quadrant? Okay, so we get negative pi over 3. Now we're trying to describe the point negative 4 root 3.
And pi.
So which radius would we need to use if we're going to use a angle measure of negative pi over 3? The positive 8 or the negative 8? The negative 8. Does everybody agree we have to use the negative 8? And so once you found one representation, again, we could find another representation. If we wanted our radius to be positive, then we just need to add or subtract pi to the negative pi over 3. But once we have one, we can get any other one that we want. So you can just verify. If I go out, imagine the polar coordinate here. If I go out negative 8 units to the left, and then rotate it clockwise pi over 3 units, that's going to give me that point negative 4 root 3. If we went over positive 8, and then rotated clockwise by pi over 3, then that's going to put us right here. That's not the point that we were after. Does all that make sense? Do you have any questions on that? All right, so then a lot of the rest of this, our notes are dedicated to looking at familiar things in the rectangular coordinates, what they look like in polar coordinates. So for instance, lines through the origin are going to take the form theta equals to theta sub 0, where the theta sub 0 or theta naught is just an angle measure. So like for example, if we have theta equals to pi over 4, that's going to be, in polar coordinates, that's going to give us a line through the origin or through the pole. So maybe we'll work with this example and then we'll write out, in general, how do we determine, how would we convert that back into a rectangular coordinate system so that we know, even though if we recognize, hey, that's a slope or that's a line through the origin, what's the slope of that line particularly? How would we measure that? So when we're given an equation theta equals to some angle measure, what we're going to do is take tangent of both sides. And then we have a means to convert. Tangent of theta is y over x. So the left-hand side is just y over x. What's the tangent of pi over 4? 1. So we know that that's the equivalent to the y over x equals 1 or y equals x. And that's how you would determine what the slopes of those lines are through the origin. So we'll write out our conversion over here. Conversion. Take the tangent. Of both sides. The equation. then write the tangent of theta as y over x. That's going to be one side. The other side which would be tangent of that theta sub 0 is just going to be a number. So whatever the tangent of that angle comes out to be. And then we solve for y. They're all lines through the origin that have that form, so it's not going to be like, they're not going to have a y-intercept that's not 0. So these lines through the origin, theta equals theta naught, will always have the form of this right here. And depending on what that angle is what the slope of that line is. So Desmos actually has a polar grid. If you go into settings and select this one, and then we can just type out something.
Can you do R first?
Like here. What was the trick here? I'm done in a minute. So most of these we can graph. Most of the ones that they say graph on your homework, you're not going to be responsible for like graphing on the final. If it's pertinent to the problem, then I'll just provide the graph because, some of these, as we'll see, are pretty intricate and they're really difficult to graph. You've got to plot so many different points before you can get a sense of what it looks like. But anyways, those are our lines through the origin, theta equals theta naught. Circles centered at the origin are just r equals to some number. So these are circles centered at the origin with a radius equal to whatever this r sub 0 is. So look at a specific example and then talk about the conversion. So if we had, let's just say we have r equals to 4. How would we convert r equals 4 back to rectangular coordinates? Hmm? So in what way?
A squared plus b squared equals c squared. And then we just solve backwards for r squared.
Okay, so but we don't have an r squared yet, do we? So that I think that's the key is using that, but we don't have an r squared. We just have r equals to 4.
Square.
So yeah, we can just square both sides, right? We're going to square both sides. And what's r squared? X squared plus y squared, right? There you go. There's your circle centered at 0, 0 with a radius of 4. So our conversion here, square both sides. And then write r squared as x squared plus y squared. That's pretty much it. So, I mean, circles take on a more natural, I guess, definition, like this one we just graphed here. If we say r equals 3 pi over 4, then that's just a circle with a radius of 3 pi over 4 centered at 0, 0. Circle of radius 5 is just r equals 5. Well, I'll just put it below. Okay, circles that are shifted, shifted up or down, r equals 2 times a sine theta, and shifted left or right, 2a cosine theta. So maybe we'll look at a specific example and then see if we can tell what's what, because I think it'll be pretty obvious. For example, let's say we have r equals to 8 cosine theta. Let's see if we can just convert that first and then try to see what we're actually dealing with. So how would we convert r equals 8 cosine theta into x's and y's? So maybe one idea that you're thinking of is based on what we did here. If I want to write r or relate r back to x and y, then I can relate it back to r squared. But the problem here is if I square both sides, yeah, I'll have an r squared on the left, which is x squared plus y squared, but I'll have a 64 cosine squared theta on the right. So it doesn't really bring me any closer to describing the right-hand side in terms of x and y. Is there any other way we could get r squared on the left without squaring cosine or squaring both sides?
Times it by r.
Huh?
Times it by r.
Yeah, you can multiply it by r. So what if we just multiply both sides of our equation by r? So now we still have r squared on the left. And we have 8r cosine. What is 8r cosine theta? 8x, right? Because r cosine theta is x. This is x. In other words, we've got x squared plus y squared equals to 8x. What is x squared plus y squared equals 8x?
When y squared plus x squared over x equals 8.
Yeah, but then we would have x's and y's on both, or x's on both sides. So how about we bring the 8x over here with the x squared? And then, right, complete the square. So y is already completed square. We can complete the square on the x, though. The x squared rather than 8x. So we've got half of negative 8 squared to complete that square, and then we have to add that over here as well. So then you've got a completed square for x. That's x minus 4 quantity squared plus y squared equals 16. So what is that? For center 4, 0, radius of 4. So let's write that out. This is a circle with a center of 4, 0, and a radius of 4. That's what our original example was, that when we write r equals to 8 cosine theta, that's what 8 cosine theta is. It's a circle with a radius of 4 and a center of 4, 0. So maybe that gives you a little bit more insight as to why they wrote it as 2 times a cosine and 2 times a sine. All right, this is so that this is our in our formula above, that's our a, that's 2 times a cosine theta. So a is the thing that tells us the radius, circle radius 4, and a also tells us whether it's positive or negative. For cosine, since it corresponds to the x, it tells us how far we shifted the circle over left to right. For sine, it's how much the circle has been shifted up or down. But the radius of the circle is the absolute value of a. Yeah.
So when A is positive, the circle moves to the right.
Yeah. Yeah, so it's even in that sense, it's more natural than, like this circle, we had to get used to our horizontal translations with x and y as like the opposite, right? So this is actually moving it 4 units to the right. But if we just look at this right here as 2 times 4 cosine, it's, it's just a direct relationship. It's not, there's no opposite relationship between the 4 and the negative 4 like we have with rectangular coordinate system. Yeah, so the radius is the absolute value of a. I guess we'll write our conversion down here. So we'll just write the two conditions, or the 2 circles down here, 2a cosine theta, and our sine theta over here. So both of these, like we said, have a radius of a. The center for this one with 2a cosine is going to be at a comma 0, whereas the center for one involving sine will be 0 comma a. So here with the center, again, we don't care. We're not paying attention to, or we're not ignoring the sign on a. If a is negative, that a goes here as whatever it is, comma 0. Or here as 0 comma a. So for example, r is equal to -6 times the sine of theta. What would be the radius of that circle? 3. So we're going to look at it like this. Radius is absolute value, but then that's going to shift the center down 3 units. So that conversion for that specific example is how we would convert all of those shifted circles. Back up here so we can write down the conversion, just a generic one. One, we multiply both sides by r. Then we're gonna write r as x squared plus y squared. Any r sine thetas we'll write as y, or any r cosine thetas write as x. And then you complete the square. All right, do you have any questions on those? Horizontal lines, y equals to b, so that's r sine theta equals to b. I don't know that these really need any conversion because it's pretty straightforward. So that's y equals to 4, right? Oh, I guess we should put a graph in here too. Let's go back to that one. Graph. So there's our shifted circle. And then we'll graph out a horizontal line as well. So that's horizontal line. What would a vertical line be? Yeah. R cosine theta equals b is a vertical line. Yeah. Spirals. So for these, I'll just, like the ones that you don't have to graph by hand, I'll just start putting Desmos or whatever next to them. So that's r equals to theta. So those spirals are actually what they call Archimedean spirals, where you have the same distance between spiral arms. It's consistent throughout. We can also look at what they call logarithmic spirals. So let's graph just r equals to theta. So there's our spiral. Notice it doesn't go on forever, and we keep changing this, this right here. It's going to change the spacing. So there's 57 theta versus 5 theta. So we'll put that one in our notes. And then, like I said, in 12.3, what we're going to do is, given, for instance, we could be given this spiral, and it might say, what's the what's the slope of the tangent line at a particular point, r theta, and we can actually compute that. So that was r equals 5 theta. So yeah, and we'll graph the other type of spiral too. So I'll do 5 theta for this one too. Well, maybe not. 0.5 theta. 0.25 theta. Let's try that. So now you've got a logarithmic spiral where, again, the spaces between the arms, if you will, aren't the same. More like a galaxy type spiral here with e to the a theta. Let's try this one. 0.25 here. Yeah. You kind of see the difference there. But again, I wouldn't have you graph those by hand, or even require you to know what those look like. It's just some of them on your homework in 12.2 will say graph this, choose the best graph. And honestly, for those, just graph them on a computer. You're not going to have to graph them by hand. I'll just mention that. Okay. Next object is cardioid. So cardioids are just a special case of these things here, pronounced limison. Son. Yeah, close enough, I guess. I don't know. And again, these things I'm not going to hold you responsible for. You've got different criteria depending on the relationship between the magnitude of A and B. You get various types of shapes. So we'll look at those in a minute. These cardioids, I would just say be able to recognize when you're dealing with a cardioid. For example, well, let me write this over here. Like r equals to, I don't know, 3 plus 3 cosine theta. Or maybe this one over here. -1 plus sine theta. So I'm not sure who named them cardioids. As you'll see, they don't. Some of them can look like hearts, but not all of them do. So let's do the 3 plus 3 cosine theta. And then we'll look at the other one just to kind of see differences. -1 sine theta. So that's the difference. Notice where that little cusp is, or I guess it's more of a corner. you know, the orientation of that depends, sine affects the y-axis, think about it that way. The cusp or the point is in the y direction, so we're dealing with sine. This little cusp or point here is in the x direction because it's cosine. But those cardioids are special cases of these here. We'll graph a couple of these too, but if we have time, we'll just perhaps run through, like, you could actually graph these things pretty easily if you recognize that it's going to have that particular form. Okay, and so for those other ones here, these two, let's look at, we'll do r as 1 minus 2 cosine theta. For this one over here, let's graph 1.2 plus 4 sine theta. So there, again, there's all those conditions. If the absolute value of A is less than B, then you've got, you know, inner loop, etc. You don't have to remember these. So once we start like finding areas and stuff, those graphs will be provided. 1 minus 2 cosine. So that's got an inner loop. I guess is what we call it.
That looks like shit.
Yeah, even if you plotted like 20 points, it's time consuming, and your graph is probably not going to look great. So we just graph it by hand or by computer. And that was 4 sine theta. Maybe we had plus, yeah.
This is the one.
All right. I mean, you know, let's just check this out in a generic sense as we vary A and B. So A is going to be fixed at 1. And B becomes larger. We've got that inner loop. If it's the same, we have a cardioid. If it's smaller, then it's working in the other direction. A that way, or A this way. It's not a circle, but it's whatever this weird thing is. And there's our inner loop. Again, just the orientation of that loop is opening, if you will, with the sine versus the cosine. Okay. So yeah, in 12.3, like I said, you might be asked to find like what's the area of this inner loop, and then if that were given to you, then fine, you can use the graph. On the homework, there are like 2 or 3 that say do this with this particular graph, and they don't give you a picture of the graph. I would just pull up a software and graph it, just so you know what you're dealing with. On the final exam, I'll have the graphs for you. Okay. So, like graphing something like this, if it says graph 2 plus 3 sine theta using in the polar coordinates, this is where you would just graph it with a computer. If that were 2 plus 2 sine theta, then we would know that's a cardioid, and we could get closer to attempting to graph that. But just as a general thing here, when we're graphing these, we want to think of r as a function of theta. When we think about the point, it's almost like by convention it was written backwards, r theta, but theta is actually your input in this sense. When you're dealing with polar coordinates, theta is your independent variable and r is your dependent variable. So if we wanted to come up with a table of values, then all we're going to do is choose some thetas and see what r is, plot those points. So we input those, we see what r is, and then we plot all of our points. You know, and you might end up with points like this if you chose a bunch of different ones. And even with whatever, how many we have there, 2, 4, 6, 8, 10, 11 points, even there it's really difficult to determine what that looks like. Because remember, when you write an ordered pair here that's like r theta, then there's multiple ways to represent that. If down this list of 100 ordered pairs, 50 of them might very well be the same point, and you're not really getting any more information that way. Do you have a question, Kevin?
No, I was just gonna ask that, like, that's all within 2 pi. So, I was thinking there was multiple revolutions for that. Probably just negative values, and that's how you get the inner circle.
Yeah.
So, is there an easy way to find, like, I guess, like the vertex of the circle, like the outer points?
No. Not that I'm aware of. I mean, other than plotting points or just knowing what it looks like, that's kind of it. I might erase these. Well, I guess we'll plot this first. 2 plus 3 sine. So there we graphed it. There we go. We're done. Okay, can we finish this one, and then we'll take a break? This is the last one. So convert the equation, r sine theta is 8 sine of 2 theta to Cartesian, describe the resulting curve. So any ideas here?
Double angle on the 8 sine.
Okay, yeah, so you see the sine of 2 theta? We want to definitely have a sine theta instead of a sine 2 theta. So that's double angle formula. Does anyone remember that?
2 sine cosine.
Yeah, 2 sine cosine. And then what else do we need to do here? Or do we need to do anything else here? Well, I guess we'll graph it in a minute. If we graph it, it's not going to actually show a portion of this graph, so let's see if that's good enough if we just rewrite 2 sine theta. So we have 8 times, we're going to rewrite this, 2 sine theta, cosine theta. In other words, r sine theta rather. Is 16 sine theta cosine theta. Okay, so we Could we divide through by sine theta here? Yes, if what's true? If it's not 0, right. We can divide through by sine theta if it's not 0. But there's nothing telling us it couldn't be 0. We know sine of something is 0 many times.
Not most of the time.
Is the left side equal to y?
Huh?
Isn't r sine theta equal to y?
Yeah, this is going to be y. This is, we're going to need, this isn't really anything over here though, right? So let's look at it like, taking, instead of dividing through by sine, let's just put both of them on the same side. Otherwise, we could break it up into two different cases. If sine of theta is 0, then we can't divide by sine of theta. If sine of theta is not 0, then we can divide through and we can see what that's going to be. But I think it's maybe a little bit more straightforward if we just bring this to the other side and set it equal to 0. Oops. So from here, we could factor out the sine. What does that leave us with? Equals to 0. So I would, just because someone mentioned dividing through by sine, I would look at it that way because sine of theta could be 0. We can see clearly here that this sine of theta can be 0.
You got an extra sign
Yeah.
Where?
inside the bracket.
Inside your bracket.
Just be 16.
Oh, right, yeah. Thanks. Okay. Otherwise, you would have to take it in two cases. If sine is not 0, then that's fine. You can divide through, and then you've got r equals to 16 cosine theta. We can describe what that curve is going to be. Or when sine is equal to 0, you've got something different happening. So two things. One, sine theta is 0. When sine theta is 0, what is that going to give us or describe for us? Maybe we'll look at this one instead. If r minus 16 cosine theta is 0, what is that describing? If r is 16 cosine theta, what does that describe for us?
That's just a line.
Well, I'll give you a hint. This is r equals to, 2 times 8 cosine theta. Circle the radius 8. Center in the x direction. Yeah, exactly. So this is a circle. Center. It's shifted positive 8 in the x direction. And the radius is 8. Is everybody okay with that? So part of it is a circle. I think the way to see this here, if sine theta is 0, look at it by multiplying both sides by r, just so we have something familiar here. R sine theta is y. Times r equals to r times 0 is 0. This is the x-axis. So what you have is actually the x-axis and that circle. We'll just summarize that here. And the x-axis. And I don't think that any software you use is actually going to highlight additionally the x-axis, so you know that it's both, but it is actually the circle and the x-axis. Okay. So I mean, I guess technically we didn't really convert this. We just kind of manipulated it and looked at it through the lens of some of the stuff we already talked about. But nonetheless, it does get us the information we need to describe what it is. Do y'all have any questions? I mean, really, there's not a whole lot on our exam over 12.2. It's just, again, like an introduction, and then 12.3 is really what we want to focus on for the final, and 12.1. Let's take a break, and then we'll start. Okay, so now, finding derivatives, we're going to look at derivatives, area, and arc length, and polar coordinates. So in order to progress, we're going to think of polar coordinates as a parametric equation. With a parameter of theta. And when we talk about derivatives, the slope of the tangent line in any coordinate system, I guess two-dimensional, any coordinate system is the rate of the change of the vertical coordinate with respect to the horizontal coordinate. Change in y over change in x, if you will. So from in 12.1, when we looked at our parametric equations, and we said that the derivative of y with respect to x was actually the derivative of y with respect to t over the derivative of x with respect to t. It was the vertical change over the horizontal change with respect to our parameter t. In 12.3, what we're going to compute for our dy over dx is similar, but our parameter is theta. So it's dy over d theta divided by dx over d theta. So if we parameterize in our polar coordinate system in r theta, we'll remember that x is described as r cosine theta. However, r is a function of theta. So we'll just write f of theta cosine theta. For x, similar for y. Since it's r sine theta, we're going to think about that as f of theta times the sine of theta. So that's what x is and that's what y is. There's a formula presented in 12.3. You can choose to remember that formula. It's going to be the same formula we come out with this. If you can just remember to parameterize x and y as such, then when we look at the derivatives, we can just base the derivatives off of basically y prime divided by x prime. So we have x prime, which is the derivative of x with respect to theta. as the derivative of this function of theta times cosine of theta. So product rule for that derivative, we have the first times the derivative of the second plus the second times the derivative of the first. The formula I don't think is intuitive. It's not, I mean, it might be easy to remember, but I think it's easier to remember it this way. Parameterize first. Y prime, which is derivative of y with respect to theta, is similar here. First derivative of the second plus the second times the derivative of the first. And so the derivative in this polar coordinate system is just y prime over x prime. dy over dx is y prime over x prime. Yeah, I guess it doesn't matter what order we write this, we'll just keep it how we have it. So that's the formula you would have to remember if you're going to just want to if you just want to remember the formula for the derivative. So it's not, I mean, it's not terribly friendly, but that is how we compute the derivative. Given r equals to some function of theta, this is how we compute its derivative. So for example, we want to find the slope of the tangent line at the given point on the cardioid 1 minus sine theta at the point 1/2 comma pi over 6. So I know the grids and stuff didn't show up very well. 1/2 pi over 6 is right here. So either remember the formula or remember how to parameterize this. The x coordinate, we'll start off with y, I guess. Y is r sine theta and x is r cosine theta. So we parameterize, just rewriting r as the function of theta that's given, or the r that's given, if you will. And then we're finding the derivative of x and y with respect to theta. So all of these are going to involve a product rule for you if you go this route. So we have the first times the derivative of the second plus the second times the derivative of the first, the derivative of 1 minus, sorry, the derivative of the first factor here, 1 minus sine theta, 0 minus cosine theta, or minus cosine theta. So that whole thing is our y prime. X prime, first derivative of the second, plus the second derivative of the first. Is everybody okay with that? Parameterize, take the derivative, then put it together, dy over dx. And you know, clean this up whenever you want, but I don't think there's a necessity to simplify this because that's our derivative. We want to find the derivative at that point. So all we're going to do once we have the derivative is plug in theta and get the slope of the tangent line at that point. So there's the derivative at any point on that curve. So we just want to evaluate this where? At pi over 6, at theta equals pi over 6. So we're just going to shorthand this, the derivative evaluated at theta equals to pi over 6. So, I mean, it's quite a tedious computation. You know, you're going to get halves and root 3s over 2, multiply those together, subtract them from one another, common denominators, all of that stuff. So, have fun with that. Answer is 0.
If you just do the top, you can figure it out faster.
Yeah, because the top is 0. It's not always. So what that means is, as we can see with the graph provided, that the slope of that tangent line is horizontal right there at that point. There's our tangent line here. So are there any questions on this? It's maybe a weird way to think about it, but either you think about it this way or you just memorize that formula. If you're going to memorize the formula, then all you need to do is figure out, given r, you just take the derivative of r itself, and that goes here and here. Everything else is given as sines and cosines or the function itself. So are there any questions on that? Is that all right? Okay. Okay. We've got a similar thing here. It says find the slopes of the tangent line at the given point, where there's actually not a point given. 2 sine of 3 theta gives us this figure here at the tips of the leaves. So the tips of the leaves here, there's 3 of them. We'll do this one, and this one. Those points are when theta equals pi over 6, 5 pi over 6, and 3 pi over 2. So y is our r times sine of theta, and x is r cosine theta. This, again, doing it this way just eliminates the necessity to memorize the formula. derivative of y. First times the derivative of the second, plus the second times the derivative of the first. So we've got 2 times sine of cosine of 3 theta times 3. We have 6 cosine 3 theta. Well, I'm probably gonna run out of room. Okay, so y prime, we need to divide that by x prime. First derivative of the second, plus the second, times the derivative of the first. Again, I wouldn't worry about simplifying it too much. You're just going to end up plugging those 3 thetas into the derivative. We have y prime over x prime.
The sine of pi halves 1. Plug in this there, times without 2, so it's pi halves. Sine of pi halves is 1. Cosine pi 6.
You know, it's just time consuming to compute these things. Especially one like this where you've got to compute this at 3 different values.
That's 0.
Honestly, this is where I would use my calculator. Something like this. Just make sure that's right. Okay. So that's our derivative. And we've just evaluated our derivative at three different points. Pi over 6. Five pi over 6. And a 3 pi over 2.
Pi over 6 is pi times. Wait, 15 pi over 6 is the same. Where's the pi?
Did anybody get any of these yet?
I got the first one.
What'd you get?
I got just a negative square root of
Negative square root of 3.
3.
For pi over 6?
Yeah. Take that with a grain of salt.
I mean, if you have a calculator, maybe try to verify.
The bottom one's definitely 0.
This one at 3 at
Uh-huh.
pi over 2. Did you compute that, or are you just looking at the graph?
Yeah, just looking at the graph.
The bottom, the at 3 pi over 2, it is 0.
Because sine of 3 theta is 0, and cosine theta at that point is also 0.
Yeah, sine is 0.
Yeah.
There, yeah. I don't know, maybe your calculator has an efficient way to just type that function out, and then say theta is equal to pi over 6. If it doesn't, it's kind of time consuming. But you should be able to come up with those results. The slope on the first pedal, negative. You see that from the graph, it should be negative. Maybe it's not root 3. Same thing here. This one's positive. And this one's 0.
1 square root of 3 square root of 1.
Okay. That's that. Questions? So sometimes these functions are easier to describe in these coordinate systems, but especially the derivative is pretty nasty. I think it's probably preferable to look at derivatives in terms of x and y versus r's and thetas. All right. Find the slope of the tangent line at the pole for cosine of 2 theta.
What's the pole?
What's the pole?
Right axis.
That's the polar axis. The polar axis is the positive x-axis.
That sucks. So wouldn't be the y-axis.
Yeah, they're all poles,
Wait,
right?
they're undefined.
No, the pole is
The center.
the pole is the origin. Theta can be anything as long as r is 0. You're at that point at the origin, the pole. So before you really figure out the slope of the tangent line, we've got to know where that 4 cosine of 2 theta, for what theta values does it actually end up intersecting?
0.
Yeah, so then we have to solve the equation. When does 0 equal to 4 cosine of 2 theta?
Let me go with pi.
So that's when cosine of 2 theta is 0. The cosine of an argument is 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. So this happens when, if you need to make a substitution, make it the cosine of alpha is 0 when that angle is pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So on and so forth. Or that's when theta is equal to pi fourths, 2 pi over 4, so on. Okay, so this one actually says find the slope of the tangent line at the pole. Now we know where theta or what angle measures give us that point there. So in order, what's our next step in order to compute the slope of the tangent line there at that point? What do we need to do? We've got the thetas. Do we need to find the derivative and then plug those thetas in? No, why not?
Because r equals 0.
Because r equals 0? So what does that do for us in terms of our dy over dx being some function of theta?
Undefined.
How come?
Because you get 0 to 0.
But if we looked at this formula here for our derivative, right, there is no r input into that, right?
Yeah.
It's just a function of theta. The derivative is another function of theta. So even though r is 0, it doesn't matter. There's nothing to plug r equals to 0 into our derivative for. But if we can think about from 12.2, what did we say that lines through the origin? All of these, the slopes of the tangent line at that point are going to be this line here and this line here, right? So if we, just going back to 12.2, we said lines through the origin. Lines through the origin have the form theta equals to some theta value, pi over 2, 3 pi over 5, whatever it is, right? We already have those theta values. Pi over 4, 3 pi over 4. You know, we could say dot, 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 but you'll see what unfolds here. There's only 2 lines that pass through the center there. Or maybe these lines here. But the point is that we have these thetas. We're talking about what's the slopes of the line that pass through the pole or the origin. Then all we need to look at is when theta equals to pi over 4, what is the slope of that line? 1, right? And we get that by our conversion. We take the tangent of both sides. And tangent of theta is rewritten as y over x. Tangent of pi over 4 is computed. Is 1. So that means what we're looking at is the line y equals x with the slope of 1, positive 1. Now the slope of the line theta equals some value. The slope of that line is just tangent of that value. So if we say then, well, maybe this other one comes into play. If theta is 3 pi over 4, what's the slope of that line? Negative 1. Yeah? Okay, let's look at the other ones that we get. 5 pi over 4 and 7 pi over 4. What's the slope of that line? 1. 7 pi over 4? Negative 1. So no matter how far we went out, past 7 pi over 4 to the right or past pi over 4 to the left, the slopes are always 1 or negative 1. So there's actually those 2 lines that we drew there. There's really no need to write other values out because they're always going to produce a 1 or a negative 1. So that's it. There's our slope of 1. There's our slope of negative 1. Those are the slopes of the tangent line at the pole. And again, we're not saying that the tangent line, at that point, right? We're saying the tangent line through the pole on this curve right here. Those are the tangent lines to that curve. So it's almost like it does have a cusp. This thing traces out maybe this way, and then comes back in here. Makes this other loop. I'm not great at drawing this, but I don't know. I just rotate it 90 degrees. Maybe it traces out like this first, comes down here and traces this, and it traces this out, and it traces that out. Right. So there's the pole, there's the tangent line, there's a tangent line to the curve. Get rid of my hideous drawing, so if that ever existed. But that's kind of the idea. Does anyone have any questions on that? As long as it's asking for the slope of the tangent line at the pole, all you got to do is figure out where does that curve intersect the pole, or when that curve is 0, and then take the tangent of those theta values you get, and those will produce your slopes. Any questions on that? looking at this as sort of a motivation, we see that there are places on any given graph here where we could have vertical tangents or horizontal tangents. So the idea is that we've got a horizontal tangent line when the derivative is equal to 0. So when all of this stuff is equal to 0, the numerator is 0, that'll give you the locations of horizontal tangent lines. When the denominator is 0, that gives you the location of your vertical tangent lines. Just like in the situation with x and y. So the horizontal tangent lines occur when dy d theta is equal to 0, and vertical are when dx d theta is 0. Now the only caveat here is that they both can't be 0. I couldn't determine if the numerator and denominator of my derivative were both 0. I couldn't say that there's a horizontal and a vertical tangent line there. It doesn't make sense. So really the caveat is, let me move these down, is that you've got a vertical tangent line. Oops. You've got a vertical tangent line when the bottom of your derivative dx over d theta is 0, and the top, your numerator, dy over d theta, is not 0. Same thing with the horizontal. The bottom, dx over d theta, cannot be 0. And we'll just say here that the slope is 0. Slope is undefined. Okay, if they both are, if dy over d theta and dx over d theta are both 0, then you've got an indeterminate form. And that's where L'Hopital's rule comes in. We won't see any of those, but the top and bottom being 0, it'll just come out in your work. You'll say, all right, well, the numerator is 0 at this theta value, the denominator is 0 at this theta value. Clearly, if they're different, then they don't coincide. It's not 0 over 0. But if you do say, well, the numerator is 0 at pi over 2 and the denominator is 0 at pi over 2 as like separate computations, then you clearly see that, hey, at pi over 2, I've got 0 over 0, and I've got to do something else. It's not like you're going to be like hyper diligent about if it's 0 over 0. You're literally going to see that unfold as you solve the problem. And we'll just stick with the circle, a little more simplistic equation, and determine on that circle where the tangent lines are horizontal and where the tangent lines are vertical. So again, what we need to do is we need to find the derivative. The horizontal tangent line occurs when dy over d theta, or if you will, y prime, is 0, and our vertical when dx over d theta or x prime is 0. So that's really what we're looking for, those two instances, which means we actually need to find the derivative first. And I guess not necessarily do we have to put the derivative together as one whole thing. But we'll go ahead and do that. So parameterize y, our cosine, or our sine theta rather, and our R is cosine theta. So R sine theta is y, and R cosine theta is x. Or, you know, if we want to write that as cosine squared. All right, so y prime first derivative of the second plus second derivative of the first. And x prime, 2 cosine theta, sine theta, or minus 2 cosine theta. So we could put it together, but really all we're after is when does y prime equal 0? That's our horizontal tangent line. When does x prime 0? That gives us for our vertical tangent or vertical tangent lines. So when does cosine squared minus sine squared equal 0?
Pi.
Where it is. I'm going to write this one out too. So how are you figuring that out? What are we using to solve that equation?
They gotta be the same.
They got it for y, yeah. Cosine squared has to be sine squared. So how does that help us solve for theta? In each quadrant, sine and cosine are the same where? Pi over 4. Yeah. So is it just pi over 4?
No, it's also.
It's also
Pi.
5 pi over 4.
It skips the second quadrant.
Right.
It's the third.
Yeah, because they're both positive in the first quadrant and both negative in the second quadrant, or third quadrant rather. So how else could you see that?
But they're squared.
Right. But even if they're squared, it's if this is 1 and this is 1, squared, 2, squared, right? It gives you the same value.
But like, it would be in all 4 quadrants?
No,
No?
just when they're same signs.
Yeah.
So is there an identity for cosine squared minus sine squared?
It equals 1.
No.
That's added.
Yeah, that's adding. All right, so maybe pause on this one. This one's a little more straightforward. You've got factors equal to 0. So this is when either cosine is 0 or sine is 0. You just write a couple of these values out. What you're going to see is that we don't need all of them, right? Because we know cosine is 0 and sine is 0 at infinitely many values. But if we're thinking about this as our shifted circle here, where this thing has vertical tangent lines, it's only at these two spots. We're just trying to find those 2 spots. So even though you get infinitely many thetas, only 2 of those thetas are going to give you a unique point. All of the other points you come up with are going to be the same, just a different way to describe them. So just write out the first few, and if you don't notice them repeating, then maybe take it out further. But So those are the theta values where we have I should have wrote this down, but this is for our vertical tangent. For a vertical tangent line. So let's just go ahead and stick with that for right now. In order to find the points, we're going to need to plug those thetas back into the equation. So we need an r and a theta. We only have a theta right now. Plugging that into, what was it, cosine theta? 3 pi over 2. And for r, and so forth. And those will give us our points, specifically these 2 points here. We just need to make sure that these are different. You know, maybe we keep going with those, maybe not. Zero in for r cosine theta. From the sine factor. Pi n. Right, so now we're actually producing points r theta. The point here is zero pi over 2, 3 pi over 2. We've got cosine of 0, which is 1, so r is 1, theta is 0. Cosine of pi, negative 1. Negative 1 comma pi. Those are the points we get. You know, and all the things that we didn't check, right? What is the point 0 pi over 2? Is that the top of the circle? R is 0. How far do you go out? None. R is the point at, when R is 0, right? That's the pole. So both of these here, the 0 pi over 2 and 0 pi over 3, are describing this point. And how about 1, 0 and negative 1 pi? Are those different points? Or are they the same? The same point, right? When we add or subtract pi to the angle, we negate the radius. So add pi to 0, negate the radius. Those are the same point. Those are the points that are generated here. So we'll describe it as that first one. Yeah, because it's positive. That's our 1, 0. Oh, sorry, 1 pi. Is that 1 pi? No, 1, 0 is fine too. So the factors or the thetas we get from the factor of cosine all produce that point at the pole. The factors from sine theta all produce that point on the left of the circle. Okay, so then we'll talk about the second part next time, the horizontal. We still need to finish this. It shouldn't take much longer. We should at least have half of the next class to review. No, I didn't. I forgot.
Can we get our test back?
Yeah, y'all want your test back? Sorry, I totally forgot you were hiding.